Hi everybody again. How are you?
Good. And
Good.
you?
Good.
Hey, you guys all see me and hear me?
Yes.
Very good.
Yeah.
Great. Okay. Um, I see that we are all the 12 people who have registered, they are here. That's a good news. So I can check all of you. But I also want to meet you at least this time. So if you don't mind, you can turn on your cameras. I think that we need to kind of start communicating with each other, and I rather see all of you and be able to say hello to you folks. I wish that I could meet you personally, but of course it is what it is. We have to stay kind of away from each other. So is this session your first session, or you had a bunch of classes earlier?
A bunch of classes earlier.
You had a bunch of classes earlier. Okay. Very good. I am going to, is Danny Hernan still there, or I don't see you? Can you please turn on your camera so I know that you're in here?
Professor, I would, but if you look at the participants list, I don't have a webcam built into my system.
You don't have a webcam on your system?
Yes, sir.
Is this Simon Yang speaking?
Yes, this is me.
Okay, so what are you gonna do for the rest of today? I mean, not
I am willing
rest
to
of semester,
participate.
I meant.
What do you mean by that, sir?
So are you gonna register, or are you registered already?
I am registered in class.
Okay. All right, so you're gonna you're gonna take care of your camera because we need your camera to be on.
Okay, I'll get that covered the next session, by the time the
Okay.
next session comes in.
No problem. All right. Because, you know, being on Zoom, as bad as it is, at least let's see each other and make sure that you are paying attention to my instructions. It is 4 o'clock, so it's not too bad, especially today wasn't that hot, so hopefully you're awake, you're not sleepy, you're not dozing off. And I would like that we have our videos on all the time. Did you guys have a chance to look at the syllabus? No? Augustine, you didn't? Okay, how about you, Emily? Yes? How about Makaila?
No, I haven't had a chance to look at it.
You didn't have a chance? Okay. Juan, what about you?
Not yet.
Not yet? It's okay. And so I suppose that we can just go over the syllabus. But before I do that, I do want to welcome you to this semester's lab, to my lab section. I'm teaching 5 lab sections. And these are all about mechanics. So it makes my job a little bit easier I don't have to repeat different things, and I don't have to prepare different materials. They are kind of easy for me, but nevertheless, it's kind of boring. I'm sure same for you, especially for the labs that you were expected, that you get your hands greasy kind of and touch the equipment and work with the equipment and measuring devices. But unfortunately, we gotta have to make do with whatever that we have. So that's the bad part. The good part of it, as I have kind of alluded to that in my announcement, is that we are going to do lots of experiment basically on computer, namely computer simulation. And the good thing about the computer simulation is that you can change the variables as much as you want. Our equipment usually in the labs are limited. The apparatus that we have, they don't have very large span or range of variables. But with computer simulation, you can do whatever you want. And you can even do the things that are not necessarily written in your lab manual. So it's all your imagination and your interest to go beyond even what we could have done in a real lab. So that's the good part. And then the other thing is that because everything is on computer and simulation, and if you have noticed, those of you who did look at the manual for the experiment today, you have noticed that the write-ups or your reports are very, very easy. Very, very easy. Because in last years, all of us, we wanted to, including myself, I especially was very interested to see that you write a full-blown report on the experiment. And usually it was 5, 6, 7 pages and lots of calculations, of course. And it was more difficult for students to come up with these well-written technical reports. Now it is the new lab format that our school has developed during summer. Lots of work has gone into it, by the way, and I have no credit for doing that, but my colleagues did. And it is much easier for you to develop your lab report. Mostly is just filling the blanks in the tables, which are already there, and so on. So we'll have a chance to look at it today. In today's experiment, we don't have any simulation because this is the kind of introduction. And in fact, we're going to have a short session today. But later on, next week and all the way for the following 11 experiments, you are going to do simulation, and I am going to work with you while you are doing simulation. You're going to generate your raw data as you would have if you were actually in a lab and doing the experiment. And then after that, once you got reliable data, then we can finish the session and you have the choice of staying to the end of the 3 hours and do the calculation and generate results and basically finish your report even if you want, or you can leave and do it at your own free time. So let me share my screen, and please communicate with me if you don't see the screen very well or if you don't hear me very well. Send me a chat or in fact, why don't you all please open your chat and send me something, just hello or hi or something, so I know that you can use your chat. Okay. So I want to make sure that if you have any questions, you know how to ask your question. Okay, very good. I think that.
I have a question.
Go ahead. Sure.
There's usually an option to take it off of private chat, but I can't seem to edit that option.
I'm sorry. Yes. Thank you for reminding these things. I do forget things, so you gotta tell me. So we have, I'm gonna turn on everybody publicly and privately. So try it now. Does it work, Makaila, now? Okay, very good. Anybody else has any concern about the way our communication? By the way, this is all being recorded, and after we finished, it will be available for anybody who wants to see and hear this session again later on. It would be available. And I put everything on your website, on the Blackboard course website. Okay, so let me get the syllabus and we can quickly go over it. It's a short syllabus. Fall 2020, 13081. Okay, and screen share. Okay. Do you guys see the first page of the syllabus?
Yes.
Yes.
Okay, very good. So here it is. This is your course ID. Monday 4 to 6:50. This is my name. My name is Abdi Majlesi, and it is read the same way that it is written. Course description, of course, the lab is really to augment your lecture sessions. It's all about mechanics, and although I have said here that you're required to have at least 75% or better in your lab grade before you pass the course, but I'm pretty sure that you're all gonna get much better than that. I've never had to give anything really less than B to anybody, and hopefully this semester will not be any exception. Okay. Lab manual. Your lab manual is already in the content area of your Blackboard, and I'm gonna put that every week. In other words, I'm gonna upload the lab manual for the experiment of that week, and I try to do it maybe 1 week ahead of time. I'm not going to put the whole 12 experiment. I don't want you to get confused and try to look at the new ones. And so I will add the lab manuals for that week that we are going to do the experiment, few days before we actually have to do it. So probably by the weekend before, when we are gonna do the lab, I'm gonna upload the lab manual. So right now, if you are able to go to Blackboard and go into content, you will see that I have already uploaded today's experiment, which is all about measurement. Policies, 1 new experiment every week. You have the total of 12. The schedule is at the end of this syllabus, and I'm going to go over it with you. The format of report, as I told you, is much easier this semester than the previous semesters. Basically, you do your analysis and your calculation and report your calculation right on the lab manual that you have, and you submit it. Your lab report is 7 days or 1 week after we have done it, and it is due before we do the current or the following lab session. In other words, you have until next week at the same time, before 4 o'clock, that you submit your lab reports. Late work is not accepted, and you have much less excuse than other times, because you can actually perform all that the lab manual is asking at your own leisure time. Okay, they're all equally weighted. Get the average of all of it at the end. And I want you to please read your lab manual before you come to the session, to the meeting, because it helps you to understand what we are doing and why we are doing, and what is the purpose and objective and all of that. If you do this, if you study it ahead of time, that's much easier. Fridays between 2 and 4 o'clock, I am available to answer any questions that you may have. It's still going to be on Zoom, of course, same ID and password as before, as your regular lab session. And this is the schedule. So today we are going to do measurement. As I said, there is no really simulation for today, but starting next week, we're going to go through the whole list of important topics on mechanics. Anybody has started the actual lecture on this course this morning? This is the first day, so I don't expect that all of you have done, but has anybody started the lectures? Yes or no? No?
No.
Okay. But I'm pretty sure that your lecture professor will explain for you that, have you taken physics before, any of you guys?
Yes, I have.
You have? Okay. At high school or in college?
High school, but it was an AP
High school.
course.
Oops, sorry about that. Let me see. Where's my phone? Turn this off. Okay, so let me just give you a little bit of background. So physics, as you probably know, is a very broad area of science. Just about everything that we do or you see around your environment has something to do with physics one way or the other. But there are some major categories in physics, and one of those major categories is called mechanics. And that's what you're going to study, or you're going to study in your lecture time, and you're going to do some computer simulations and discussions in your lab sessions. Who knows what mechanics really deals with? In a couple of maybe sentences or one sentence. Okay, I'll tell you. Mechanics deals with motion. Anything that has something to do with moving objects or particles falls in the category of mechanics. And that's what you're going to study in your lecture time, and we're going to do simulation and discussion in the lab. So this list that you see in here, experiment number 2, one-dimensional kinematics. And I'm going to discuss that when we get to it. The third week is Labor Day holiday, so nothing there. And then we talk about vectors. These are a special type of physical quantities, and we see how they are added and subtracted from each other. We're going to talk about something which is very familiar with all of you, as free fall and projectile motion. When you're throwing something in the air, not necessarily upward, but in a slanted way, when you're sending something, that's a projectile motion. Then we talk, of course, about the causes of motion, which is force. That's the cause of motion. Momentum, another physical quantity. Very important part of physics is conservation principles. Some things never change, and one of them is energy. So maybe to your surprise, the total energy in the universe is fixed, is constant. And that is what the energy conservation, or the principle of conservation of energy, is all about. Then near the middle of the semester, we get to rotational motion. And then we are going to talk about very simple repeating motion, such as the motion of a pendulum, or which is very similar to the motion of a swing, just goes back and forth. So we're going to study that. And a special type of this type of repeated motion is called simple harmonic motion, SHM, simple harmonic motion. And that's another very general and very broad area of the oscillating motions. Then near the end of the semester, we get to the Newton's law of gravitation, which is a universal law. So it is good not only on Earth, but on any other planet, anywhere in the universe that is applicable. Then we talk about waves. And finally, we have a discussion on how fluids move. So it's all about motion, and that's why it is called the mechanics. Now, I also have written here some ideas to help you making sure that you get a good grade and you develop a very accurate and professional report. Of course, unfortunately, you are limited because I don't expect you to write everything yourself and give me a, 5, 8, 10 pages of what you write. But nevertheless, when you're submitting your report, which is basically writing in your lab manual or the result of your lab simulation, you got to pay attention to the following. First of all, because I'm teaching so many different sections, make sure that on your first page, where you are writing the title of the experiment, the date it was performed, your name, and then you also make sure that you put the section number so that I can organize the reports that I get. Most probably, I will open up a session in your Blackboard so that you can submit your report right into that section or into that area. And so it would be automatically organized. But nevertheless, make sure you write your section number. And if you are producing data, if you're producing the tables separately than what is in your lab manual, and if you're producing graphs, please make sure that you follow these or pay attention to these important materials. And I'm gonna say this once, and it's here, hopefully you remember. Every table that you produce, it must have a table number and a table title written right above it. And the reason for that is that in the text of the report or any technical paper, you may want to refer to that table. So it has to have a name. And also, if a reader is looking at your table, he or she should find out or should realize what is this data all about. So that the title will give you that. Make sure that your tables have, or the quantities in your tables, they have units. For example, you're measuring something you're measuring lengths of something and you're putting some numbers in a column. If you don't say what is the unit of those numbers, it's completely ambiguous. It could be 5, but is it centimeter? Is it inch? Is it meter? So that's extremely important, and that's a pitfall. Some people forget to do that and they lose points. Then of course, every calculation that you do, I'm gonna double check. So I must have a sample calculation so I can see what you have done. And your results, which is basically the outcome of the experiment, is the fruit of all these attempt, and the activity is the results. And the results are either in the form of a table or in the form of a graph. If it is in the form of a graph, the graph must have a figure number and a figure caption, just like the table. So the figure caption tells the reader what is this graph all about, what is it showing? And it must be below each figure. These are a standard way of producing tables and figures. In all technical articles and papers, you will see those. Your graph, of course, is going to have axes. Axes must have tick marks. They must have label and unit. And when you get to the conclusion and discussion, please do not ever give me a report without some type of discussion of the results, some type of conclusion. What is these results? What does that show you? What do you understand? You have drawn something and one variable versus another variable turned out to be, let's say, linear. You can't just leave it like that. You got to say that, okay, these two have a linear relationship and they match, this behavior matches the prediction by the theory, or it doesn't. If it doesn't, then there are some errors. And then you got to discuss in your discussion the sources of your error. If there are any references, I'm going to discuss that later on when we get to it. You gotta list those references so that you will not be copying something from somebody else's work, because your report is your work. So it has to be produced by yourself. If you are borrowing something from somebody else, it must have a reference so that the credit will be given to the original provider. And then there are, of course, questions at the end of or in the middle of the report, in the middle of your, lab manual. And so you need to answer those. Sometimes the questions are already in the middle of the report. So it's already been answered by the calculation. Sometimes they are specifically or very clearly, they're at the end of the report, and then you're gonna answer those questions. So basically, this is very simple syllabus. Any questions any of you have?
So just to clarify about the labs, so say we had a lab like today, or like, I guess, yeah, so say we had a lab today, from our discussion from our lecture, then that next following Monday, the lab would be due, correct?
So if you have, if you have something, today's experiment doesn't really follows the type of reports that I usually see, because it's everything you answer right in the report. So there's not much discussion, nothing very particular. It's all about what is already explained in the report. And you just, there's a couple of calculations that you can do, and I'm gonna help you do it, at least one of them together, so that you know how to do it. So there is really not much to discuss. But as we go forward, there are experiments and simulations that you will do, and I want you to discuss them. If there is no space in the lab manual itself that you write your discussion, then you just write it separately and you attach it to the rest of your report. Did I answer your question?
Yes.
Okay. Anybody else has any questions? Okay. So now let's look at today's experiment. So today's experiment is all about the measurement. Okay. Let me see if I can make it larger. And so you guys see the first page of this manual.
I don't see anything.
I have frozen on my screen.
Yeah, neither do I. It's frozen.
You
Yeah.
see that it says measurement laboratory?
No.
No?
No.
Okay, let's.
Stuck on the syllabus. Like
Yeah.
you transitioning
Oh, you're
from
still on the syllabus. Okay,
Yeah.
let me correct that. Just bear with me, please. What do you see now?
It's still frozen on my end.
Same here.
You're still seeing the syllabus?
Yeah.
What are you seeing?
I'm gonna take a screenshot.
The
Wait.
syllabus.
Yeah, it's like you closing the page and it's like that transition.
Yeah.
So
Oh.
yeah. It's like you click to minimize it.
I know,
Yeah.
because I see, because I have my iPad and my computer on at the same time, and I think there's something went wrong with my iPad. So let me turn this off. And start again. Why is that? Okay, well, let's not worry about that. Do you guys, is it any better now?
No.
No?
No.
Huh. That's amazing. I turned off the iPad that had that thing on it. Okay, the only thing I can do is maybe get out and come back again. So,
Professor,
yes.
on your Zoom taskbar at the bottom, does it still say share screen?
Yeah, and it tells me that I am sharing.
Try
Try
unsharing.
unsharing it and then reshare the window that you're trying to show us.
So maybe I stop and then share again.
It's working now.
How about now?
We can
It's
see-
working. It's
Yeah,
good.
yeah.
You can see it.
Okay. All right. You see that it says measurement laboratory
Yes.
with the Excel thing. You see that?
We see it.
Yeah, we see it.
Okay, great. Thank you. All right. So I take it that most of you are familiar with Excel. And so what Excel does is that it is basically a spreadsheet, which means that you can enter data and then you can manipulate those data. So there is, I read that, and this is a very good tutorial of how to actually enter the data and create other things with it. So instead of just reading this, the whole thing for you, I'll let you do it at your own leisure time, at own free time. If you don't know it, I take it that most of you have already used Excel. Has anybody used Excel?
I did, but I think I forgot most of it.
You can answer with chat too if you like. I want to get a feeling that
Professor,
how many of you have used Excel?
is it fine for, in this case, could we use Google Sheets?
You can do what?
Use Google Sheets, which is the same, I think it's a Google equivalent of Excel.
Yeah, it is just a, if you have Microsoft Office, which I think you probably have it, and you go into Excel, and it will give you different sheets, sheet 1, sheet 2, etc. And all it is that when you open it, it gives you a blank. I think there's something wrong with my iPad, so I cannot use that at the moment. But it's very easy to do. You go to Microsoft Office, which has a suite of different programs. One of them is Word. I'm sure you have used Word. The other one is Excel. And Excel is a spreadsheet, which means that it allows you to enter data. So, for example, let's say you have, in this example that the tutorial is giving you, and I'm sure you can just follow this by yourself. you give a bunch of numbers. Let's say this is a one variable and this is the other variable. One variable is distance in this case. So basically you have a table and you're populating that table. And so as you can see, the very first row on the table on that each column is the name of that variable, and it must have a unit. So you can see that, that's why I emphasize that. So you enter these names and the numbers that you have generated. These are your raw data. Let's say you have done one experiment, you have measured the distance that a moving object has traveled. So I've measured the distance and then how long it took, how many seconds it took until that object has traveled so much. So after 9 seconds, for example, here, you'll see that it has traveled 88.2 meters. You guys see my cursor as I'm using it?
We see your cursor.
Okay, yeah, I'm moving my cursor, so I hope that you can see it. All right, so that's what this is all about. The Excel basically creates a table for you. Now, you can also manipulate this data by using some type of function. And function could be as simple as, let's say, adding each entry of the first column to this entry of the second column on the same row. Or you can multiply them together or divide and so on. And you can do that by expressing basically a function in here. For example, suppose that you want to divide the distance by time. So what are you going to get if you divide distance by time? Anybody?
Isn't that velocity?
Velocity.
Yes, exactly. This would be the speed or velocity. And so you want to do that, okay? And so here's at t equal to 0, the distance that the object has traveled is 0. So this is just at, let's say, at the origin of a coordinate system. The object is sitting there and time equal to 0, and then it starts to move. So suppose you want to find the velocity. So you come in here, you create another column, column C, under velocity. You write velocity meter per second. And now you want to use, for example, this row data of the row 2. Distance is 9.8, time is 1 second. And you want to find what would the velocity within the first second of this moving object. So in order to do that, of course, you're gonna divide this number 9.8 by this number 1. Now, each of these numbers have a location in this table, and the location of this number 9.8 is in the column A and row 2. And so you see here is the location of this 9.8 number is basically A2. So you want to get whatever which is in this location of A2 divided by the quantity which is in this other cell. These are called cells. And this cell, number 1, is located in the cell of B, that's the column first, and then row 2. So that's B2. So instead of just looking at the numbers, you look at what is in the cells that contains those numbers. So A2 means 9.8, B2 means 1. And you want to divide this together. So you need a function, and this is the function. So you click on the function, or you just come in here, click on this cell, which is going to be the result of dividing 9.8 by 1. Click on that, and you go up in here. So you have basically saying that I want to put the number in this cell. Now, what number goes in there, you put that up in here. And when you start up in here with this equal sign, that just means the function, this f of x, for example, the function is equal to, and then you do whatever the operation you want to do. You want to divide this cell by this cell, so A2 divide by B2, and then enter, and the computer just follows your instruction and divide this number by this number and puts it in here. Now, for the next operation, you want to do now divide this data point by this data point, still the continuation of this experiment. And now you don't have to do this again. You don't have to say now, put your cursor in here, click, and then go up in here and say, I want to divide now A3 by B3 or A2. You did A2, okay. A3 divided by B3. You don't have to say that again. All you do, you just bring your cursor at this corner, which looks like there's a rectangle, black rectangle in here. Get your cursor in there and just pull this down. As you pull this down, the same operation that had happened in this cell is going to repeat everywhere else. So automatically this number gets divided by this number, and you're going to see that appears in here, and then this number 88.2 device is going to get divided by 3 and it's going to appear in here, and so on. So very quickly, as it's shown in here, when you pull that little rectangle at the corner of that box, of this box in here, as you pull it down, and this is what it's shown in intermediate, is pulling this down, and then when you let it go, it is going to create all these results automatically for you. Okay, so that's, you can do any sort of simple or complex function on these two columns. Or maybe you have 3 columns and you want to create a 4th column by doing that. So you can do all sorts of things, but the easiest thing is what I just explained for you. So that's creating a table. Now, suppose that you want to plot one variable versus another variable. So I think some of you already know, but in Excel, all you have to do is just first highlight these two. I'm going to plot, let's say, let me see which one's plot versus what. Yeah, you want to plot the first column versus the second column. So you highlight these two columns. Don't worry about the velocity. You're highlighting these two columns. Basically, you select these two columns, and then in here at the tool area in here, you can click on insert, and by doing that you can create a plot and you can insert it in a screen within the original screen. Okay, you can see this right in here, and you got to kind of follow this tutorial to see each of these functions. But it's very easy that you can create a plot of these numbers versus this number. By the way, whenever you say versus, the quantity that comes after the word versus always goes in the x-axis. Okay, x-axis is the horizontal axis, and so in here it is plotting distance versus time. So time is called your independent variable, and in this case distance is your dependent variable. So independent variable always on the x-axis or horizontal axis, and dependent variable on the y-axis. So you're plotting in here the dependent variable, which is distance in here versus independent variable, which is your time. And as soon as you do that, of course, there are different ways that you can plot these two variables versus each other. And it gives you all these different options, gives you all these different ways of plotting. And the scatter plot is usually the one that we always use, like that. So you can, I'm not going to explain this because you got to read this very easy tutorial, and you can see that you can change the scale on the x-axis, you can change the scale on the y-axis, you can easily add a label on basically the name of this variable and name of this variable. You can even change the name of the table or add the table name, and all of this is in here. So I'm going to skip the actual working with Excel. I think you should learn it by yourself. Now, something that I want to explain for you is uncertainty. Uncertainty, this word in here, uncertainty in measurement. Let me explain for you that every measurement that you and I do are erroneous. They have error in them. Simply because we don't have very exact, very nicely calibrated apparatus or measuring devices that we can measure physical quantities very accurately. So basically, you can believe that everything that we measure, it has some error in it. That error, we can call it uncertainty. Why? Because when you measure something, let's say the length of a pencil, and you take, let me try to reopen my iPad, see if this time it will allow me to draw it in here. Not this one. Zoom. Let me see if it works this time. Okay, let me do something here for a minute. Hmm. Okay, well, I can't make it to work, so forget it. Let's start sharing the screen again. Okay, so we're talking about uncertainty. So what is uncertainty? Uncertainty, as is explained here, do you guys see the screen?
Yes.
Yes.
Yes, okay. The uncertainty is the true value minus the best measurement that you have done. The best estimate, that just means the best measurement that you have done. And then you divide it by the true value times 100, and that is the percentage of uncertainty. Some people call it percentage of error or percentage of discrepancy. They're all meaning the same thing. Okay, so you inevitably you are going to have some type of uncertainty in your measurement because of the limitation of our measuring device. So now going back to here, to this graph in here in Excel, there is only a function that you can activate, and Excel will pass a curve through your data, okay, any of these curves that you see. And one of those curves is just a linear curve, which is a line. And because most of the time there is a linear relationship between the variables, it may turn out that the result of your measurement, let's say, if you're plotting in here, let's say in this case, I think it is plotting velocity. Here's the velocity versus time, I think. And let me see. No, it is, yeah, versus time, or no, versus distance. It's plotting, yeah, velocity versus distance. And these are how many data points we have in here. We have like, we have 9 data points in here from 1 to 9. And it is plotting those in here, these 9 data points. And if you pass a line through them, you will see that all these data points are actually falling along a straight line. In other words, this straight line will cover all these 9 data points, ensuring or telling you for certain that your variable velocity, if it is plotted versus distance or it is varied versus distance, is going to give you a linear relationship. Now, and then Excel also gives you the equation of this line if you ask for it, which is again described in this tutorial. For example, it's shown in here that the equation for this line is y. Y refers to the dependent variable, is equal to 9.8 times x, and x is your independent variable, which goes along the horizontal direction, minus 3 times 10 to minus 14. So basically almost 0, right? Very small. Now, Excel also gives you this quantity, this factor of R square. What is R square? R square is basically tells you how good this line really covers all the data points that you have used. Namely, how good is the estimate that all these data points represent a line with this specific equation. And the closer that R2 is to 1, the better is that approximation. More exact is the approximation that this line really represents all these data points, this line with this equation. So if you ask, the Excel will give you the equation. It also gives you how good the equation is representing this relationship between velocity and distance with this number. And as I said, the closer that R2 is to 1, the better is the fit of that line with those data points. By the way, this line is called least square feet, which means that the distance between each of these data points and the line is minimized. Namely, Excel automatically comes up with this equation in such a way that the deviation between these data points and the line added plus the deviation between this data point and the line, and the deviation or distance between this data point and the line added together is minimal, is the least possible. That's why it's called least square. Now, what is the square comes into the picture is that deviation, namely the distance between data point and the line, it could be a positive number if the data point is really above. Let me see if I can make this even bigger. I think there's a limit to how much I can enlarge this. But if you pay attention, you see that some of these data points are slightly above the line, and then some of them are slightly below, like this one. Data point number 2 is slightly below the line, and this one is slightly above the line. Now, if the one which is above the line, this deviation or this difference is going to be positive. This deviation or this difference is going to be negative. And if you add them together, they may cancel each other out. Whereas in reality, this is erroneous and this is erroneous. So they really have to be accounted for. So what the program does, it takes this deviation and squares it. So if it is positive, it still becomes positive. And this deviation, which is negative number, because the data is below the line, really, that deviation is squared, becomes also positive. So we have so much error or uncertainty here, and so much error, also uncertainty in here. And these two uncertainties or these two errors, they are not going to cancel each other out, because that's not good. If they cancel each other out, they could be really far away from the line, and yet the net error would have become 0 if you then square those two values. So you first square them, and then you add all of them together, all of these deviations squared for all these 9 data points, and add them together. And now, if you change these numbers of this line, namely the slope and the other part, if you change them, of course, the direction of this line is going to change, and therefore these deviations are going to change. And Excel does it automatically. It keeps changing that until it gets the minimum amount of error between the line and all those data points. So it basically gives you the best fit, the best possible fit between the data points and the line. That's why it's called least square fit. Okay, so that's that. And so we talked about the uncertainty and all of that. R2 is indication of how good the line and data points they match. The best is R2 equal to 1. And then there are other things that unfortunately I cannot show it to you. I'll let you play with it. But instead of, when you're measuring the lengths, instead of actually taking a ruler and measure it, which is not very accurate, by the way, what is the smallest graduation on a regular scale? A ruler, which has metric tick marks on it. Anybody remembers? Okay, Do you guys see this? Yes or no?
We see it.
Yes.
Okay. This is the bottom part is inch, the top part is metric, is basically is centimeter. So you see these numbers 20, 21, 22, 23, these are in centimeter. But you also see that there are smaller graduations. And those tick marks, if you
Or
count
millimeters?
them, what is it?
Millimeters?
Yes, exactly. Those smaller tick marks, they are millimeters, okay? And so the smallest graduation on a measuring device indicate the resolution of that measuring device, okay? So this ruler that I have in my hand has a resolution of 1 millimeter. And of course, you know that if you're, for example, measuring the thickness of your hair, it's not a good idea to use this ruler because its resolution is so limited. Instead, there are better devices such as a vernier caliper. This device is called a vernier caliper. And vernier is the name of a French scientist who invented that. Caliper, of course, just means caliper, is measuring tool. And so that you can use, and it gives you, if you can see it in here, it gives you to 1/100th of a millimeter. So it can give you 100th time better resolution as a regular ruler. On the right side, there's another device, and it also gives you to, I believe, 1/100th of a millimeter. Yes, 1/100th of a millimeter. Actually, I'm sorry, it is much better than that. It says in here 1/10,000th of a millimeter. Can you read these in here? I tried to magnify this picture, but I'm not sure if you can see it. But right here it says 0.0001 millimeters. So 1/10,000th of a millimeter is how much it can read. So for example, right now, what it is reading, let's say 0.0127. So anyway, so you can use these. This is called micrometer. This is called vernier caliper. And if you click on these hot links, it will take you to a YouTube video that tells you how to read the numbers, how to measure let's say the thickness of one page of paper or the thickness of your hair by using these other very precise measuring devices. Okay. The next thing that we want to discuss in here, that's the end of it, is called error propagation. Error propagation. So suppose that, let's look at this example in here. So suppose that you're measuring a rectangular box, and I'm going to be done in about 15 minutes or so. Suppose that you're measuring a rectangular box, and let's say the length of the box is 8.4 centimeter, okay? Width of it is 4.7 centimeter, and height is 3.2 centimeter, okay? And we want to find what is the volume. Of course, volume is length times width times height. So here is length L times W, width times height h. And it turns out you multiply these together, you get 126.3 centimeter cube, correct? But as I told you, every measurement that we do is erroneous. It has so much error in it, maybe very small, but still there is some error or uncertainty in it. So 8.4 that you have measured is not really 8.4 because of the limitation of the resolution of your measuring device. And it could be whatever this number is plus so much or minus so much, right? So that's the range. So 8.4 plus or minus 0.05 centimeter. Okay, please note that the length in centimeter, uncertainty also in the centimeter. So by the way, how many millimeter is 0.05 centimeter? If you wanted to convert into millimeter. Anybody?
Is it 0.127?
It would be, yeah, it would be multiplying this by 10, so it becomes 0.5, right? Half a millimeter. 0.5 millimeter is 0.05 centimeter because you know, the metric system, every time that you go one notch down or one notch up, you got to multiply by 10 or divide by 10. So here is 0.5 or 0.5 millimeter or 0.05 centimeter amount of uncertainty. So by the way, the amount of uncertainty, I don't know if it says in here or not, but it is written like this. Yeah, like this. So for example, you have 8.4, right? 8.4. And then the uncertainty of measuring this length is this number. So your actual length is equal to 8.4 plus or minus 0.05, and everything is in centimeter. I usually put the units in parentheses to show that these are the units. Okay, so that is how you write it. Okay, so in this case, now I'm going to come back to these equations in just a minute, but all right, so in this case, you have these numbers in here. Where is it? These numbers. Right there, 126.6 is the volume, but what is the amount of error in this number? Okay, we know that this number, volume, is erroneous because it came from calculation of h times width times length, and each of these three numbers themselves are erroneous, and therefore the multiplication of them, which is 126.3, is also erroneous. Now, how much error is in there? The amount of error in there is not going to be simply 0.05 times 0.05 times 0.05. It's not going to be that. You're going to have to use this equation right in here, write this equation, in order to find the amount of uncertainty that is developed in the final result. And the way you do that is like this. I mean, this equation comes from expansion of Taylor's series, which I'm not going to discuss with you. It takes a long time. But This equation gives you the amount of error that has propagated through this calculation coming from individual errors of this height and width and length. So partial of f with respect to x, it basically tells you get differential of the function with respect to the first variable. You see here, volume is a function of length times width times height. So volume is a function of three things: length, width, and height. So that first term in here tells you get the derivative of v with respect to L. Okay, derivative of v with respect to L. Well, you have taken, all of you have taken calculus, correct? Yes or no?
Yes.
You have taken calculus. So you know that derivative of this function v with respect to L is going to be just a multiplication of the other two.
Yeah.
Right? So you multiply width times height, right? W times 8, 4.7 times 3.2, and you're going to get this number, 15.04. Okay? That's partial of f with respect to x, namely, you get differential of the volume with respect to L. And then this other term, differential of the function v with respect to the other variable, is w. And so it shows right in here. Differential of v with respect to w just becomes this multiplication of the other two variables, L times h. So here's L times h, which is 8.4 times 3.2. L times h, and that becomes 39.48. And finally, the last term in here is derivative of volume with respect to height. So it becomes L times W right here. L times W, you multiply these two numbers. L is 8.4, W is 4.7, and you get this number. So then you take each of these numbers that you got, you square it, and then multiply by what? By delta x. Because you were taking derivative with respect to x, you're going to multiply by delta x. What is delta x? Delta x is the error in measuring the variable x, the first variable. Okay, so your first variable, length, here it calls it xyz instead, or xyw instead of length, width, and height. Sometimes I wish they had called it xyz. Anyway, so this delta x is the error in the first variable. How much was the error in the first variable? 0.05, correct? And square it, plus this part. And delta y is error in the second variable, square. And then the last one is the error in the third variable. And if there are more variables, then this continues. But of course, we have only 3. So you do all of that, and this is what you'll get in here. Here is length, first variable, width, second variable, and height, the third variable. And we already calculated this value in here, 15.05 is right here. You square it times the error in length, 0.05 squared, and then the same thing for the other ones. And these are all squared. So you got to get a square root of it to get the actual error. So you get the square root of it, and that becomes 2.5 centimeter cube. So that is the error of this quantity, which is the volume. So if you want to write the volume, how would you write it? What is the value of the volume now?
Would it be that 126.3 centimeters cubed plus or minus the 2.50 centimeters cubed.
Exactly. Yes. You said it. Yeah, so volume now becomes equal to the nominal value. This is called the nominal value in here. And all of these are the nominal values. So it's going to become 126.3. And then you calculated the error propagation, how much error propagates through this equation, because the ingredients of this equation, if you will, they are erroneous themselves. And that turned out to be 2.5 plus 2.5. And everything is the unit, of course, of centimeter cube. Okay, that would be the volume. And you can do this for a let's say for a cylinder or for a sphere. Here's for a cylinder, for example, and it wants you to do it. Is it the same as that? 8.4. Okay, this is just a rectangle. Let's do this together. It's a cylinder, and let's do this together. Are you guys ready?
Yeah.
Okay, so cylinder volume is pi times r squared times h. Okay, and we know the value of diameter, so r, basically half of that. Height is h, and pi doesn't have any uncertainty. Pi is just pi. So, but the uncertainty of diameter is this much, uncertainty of height is this much. And you can see that these are different numbers. This number in here and this number in here are different, and that means that they have been measured with different measuring device. So let's calculate what is, let me get my pen, and then I'll let you go. Okay, first let me erase these parts. Don't need these. Okay, now draw. Okay, so we have, this is our equation right here. I'm going to get partial of v with respect to the first variable, let's say with respect to h. That's very easy. How much is that? Anybody? Pi times what? R squared, right? Because you are taking derivative with respect to this variable. Are you guys awake, or did I put you into sleep?
No, I'm good.
You're awake? Good.
No.
So that's that. What about partial, maybe differential with respect to r?
It would be pi times height.
It's going to be pi, right? And derivative of r squared is what?
2r.
2r, exactly, thank you. And then, of course, h is just h, because these are not changing. Okay, so that's that. So this becomes equal to pi. Now these are all, of course, the nominal values. Diameter is 1.51, so r becomes half of that. 0.7. What is it? 5 and 5. Is that correct?
Yeah, that's correct.
Okay, so this is times 0.7. By the way, this is your sample calculation. This is what you have to do, and then once you did the calculated this and you put all the numbers, then you submit it to me. So you don't have to write anything else. This is very easy lab report this week. So this is just that, you calculate this. And then here is equal to pi times 2 times r is basically diameter, right? So it's 1.51, 1.51, and then times h. H is 6.35, 6.35. Can somebody calculate these? I'm gonna do the same to just make sure everything is correct. 0.755, then a square times pi. I got 1.791. And this one, I may as well square it because we got to get a square of that. So partial V, partial H. This is H. The whole thing is squared is equal to this number that I just got squared. 3.21. Does anybody else got this number?
Why did you square the answer?
You got this or no?
I got 1.79, but I didn't get the 3.21.
Okay, let me double check this then. I have pi times r squared, right? So pi times r is definitely 1 point, this is that. So let me double check that. 0.755, and then a squared, and then times pi. Yep, 1.791, and then a squared again. And I think this is correct. I got 3.2069, which is approximately 3.207, maybe I should say. That would be 4 digits. So with 3 significant digits, it's going to be 3.21. So I'm going to leave it like that. And the other number down in here is pi times 1.51 times 6.35, and they're all in centimeters, so everything is correct. That becomes, I have 30.1, and then squaring it, partial V, partial R, squared becomes this number squared, and squared, and I get 907.4. Okay, so you putting all of that into this equation in here, which came from the Taylor series, the amount of uncertainty of, this is called delta or uncertainty, you can call it this way, of the volume is equal to square root of this number here, right, squared 3.21, and it should be multiplied by the uncertainty of the first variable. Our first variable, I take it to be h, doesn't matter which one you take first, but the uncertainty of H was how much? Height, sorry, here. Height uncertainty 0.00, no, I'm sorry. This is the first one is the radius. Uncertainty is 0.0005. Okay, so oops, right here. So times, I gotta do this again. Draw. Okay, so times 0.0000. Was it 4 zeros or 3? I forgot.
It's 3 zeros.
Okay, 3 zeros and then 5 and then a squared plus the uncertainty square of the second variable, which was already squared it, so it is 907.4 times the uncertainty of H, which was 0.005, I think, it was like that, squared, and then square root of the whole thing. And that becomes equal to, so let me calculate this. So that is times 0.005 squared becomes that plus 3.21 times 0.0005 squared becomes that. And then we've got to get the square root of it. So the total result becomes, the final result becomes 0.151 centimeter cubed. Okay, so that is the unit in here. And therefore, in this case, you can write that the volume is equal to, oh, we didn't calculate the actual volume. Actual volume is given by this relationship in here. So it is pi times the nominal values in here. I have, this is diameter, this is the radius, right? So it is pi times radius, which is 0.755 squared, and then times the height, which is 6.35. So that's 11.37 plus or minus 0.151. Is 1. Everything in centimeter cubed. You got it?
I have a quick question, or a couple of questions.
Sure.
So one of my questions was, when you took the derivative of the volume, oh, I'm sorry, is my mic off? Can you hear me?
We get, for the derivative, here's your derivative, right?
Hello?
Pi r square h. And we know that pi is really not changing, namely, there is no error in pi. So the error that propagates to the calculation of volume comes from two places. One is from r, and the other one is from h, correct? So you take derivative of volume with respect to, let's say, h. that just becomes the rest of it, right? It's just like you have a bunch of coefficients, and then you have times h, and then this is v equals to that. So dv dh, right? dv dh, it just becomes those multiplication of those variables. So this variable here times this variable here. Because when you're taking partial derivative, you're assuming that these are constants. And the only that changes is this one. So this just becomes coefficient, constant, so that just becomes this variable times this variable. So in this case, just becomes this variable in here times this other variable in the equation, in this equation of pi r squared times h. So you get that, and then this becomes partial v partial h, but you got to square it to put it in here. And then with this,
that was my question. I'm sorry, I probably didn't explain it right, but I just wanted to know why you had to square the derivative. Like when you took the derivative, why did you have to square the answer?
why do we have to square it? Oh,
Yeah.
oh, okay. It is because of the fact that, let me get rid of this in here, going back to this equation that we have. Right there. Either this equation in here, this equation, or this equation, which is relates to this problem. So, you know, when you have a function of several variables, what is delta f over delta x? What really does this parenthesis mean? You have a function of f, and f is a function of x, y, and let's say w. What is derivative of f with respect to f? What is df dx? What does that really represent geometrically? Anybody knows? What does derivative geometrically, what does it indicate?
Is it? Would it be?
Doesn't that indicate the slope?
Slope of the tangent line.
Yeah.
Yeah, it indicates the slope. So if you have a function of, let's say, x, and you plot f df dx, or you plot f over x, that ratio is basically the slope of the function. Now, a slope of the function, let me try it for you here. Annotate and draw. Guess you have to do this and then do this. Okay. So df dx, that really means a slope, correct? So if f is a very strong dependent on x, then the slope is going to be high. This is f and this is x, which means that any change in x creates a big change in f. If the slope is low, is a small, let's say this is like that, then a small change in x from here to here is going to create a very small change in f, correct? And if df dx is 0, the slope is 0, so this would be f again versus x, then this relationship has a slope of 0, which means that f is not really a function of x. You change x, and the value of f Doesn't change. It's still the same number. No matter what is x, the same number. So the slope indicates what is the sensitivity of f with respect to x. And then if you multiply df by dx without squaring it, okay, that really indicates the sensitivity of f with respect to x. And then you multiply this by delta x without squaring it, by delta x. Now, what is delta x? Delta x is the uncertainty in x. This is basically the error that you did when you were measuring x. Correct? So you multiply the error of x and you take the error of the x and you multiply it by sensitivity of f with respect to x. So that whole thing becomes the error of f, the error of f because of the error that was in x. And then df dy against sensitivity of f with respect to second variable, you multiply by the error in the second variable. Without squaring it, that gives you the amount of error in f because there was so much error in y. And then the same thing for other variables. And you can add them together to get the total error of f because of the error in x, because of the error in y, because of the error in z in the other variables. But if you don't square them, one of these may be positive and another one may be negative. And then they may cancel each other out. But that is very misleading because there's so much error in here and there's so much error in here, and they really should not cancel each other out. They should add up together because they are both error. So total error should be the summation of a bunch of positive numbers. That's why you square everything. You square this part to become positive, you square this part to become positive, and the rest of the variables. And now these are going to be always same with the same sign. So they're going to always add up together, and that's what you want. However, you really don't want the square of them. You got to get the real error, not the error squared. So that's why after you did that, then you take the square root of it so that you come back to the power 1 and not the power 2. You come back to the actual error or not, and not the square of the error. So that's why I made this very long, but that's why you square them, because you don't want that some of these quantities be positive, namely, for example, this quantity be positive, and then the same thing with respect to y would be negative, because instead of they really add up together, they're going to cancel each other out. And that would be, you think there is no error, but in reality, if all the ingredients are erroneous, then the total is going to be erroneous as well. So you're trying to avoid such scenario. Did I answer your question?
Yeah, thank you. And also, the little sign before the square root, is that the symbol for the error of uncertainty, or?
When you get the square root of the total, that is the square of the volume. But when you're looking at each of these quantities, you can think that they are a square of the area. So, I mean, you can think about, of the error of the area. So if this is a cube like that, I'm using a cube like this, then the error in here times the error in here, or add to the error in here and then add to the error in here. So because they become a centimeter square, so they really represent some type of area. So when you square them, you are taking into effect or taking into account the error in this length times this length, and then add to that the error in this length times this length, and then add to that the error of this length times this length. So then, of course, you gotta again get the square root of it. Is that okay?
Yeah, yes.
All right. So then you can do that for a sphere. There's one for a sphere in here. You can do it yourself. And this is the same thing, error propagation again. And it wants you to calculate, plot it. Now this is a real data, okay? Time, distance.
Professor,
Let me finish. The uncertainty in time and the uncertainty in distance. And you divide to get velocity, and in the same way you gotta find what is the uncertainty in velocity. Yes, question?
I'm sorry to interfere, but
That's okay.
is this document the same one that's on Blackboard?
Yeah.
Because
Exactly.
I downloaded the file and it's not the same.
Yeah.
Didn't you download the one in the content area?
Yes, in the contents.
It has to be.
Because your document just says measurement, while the measurement file that's on Blackboard is a modified version than the actual one, which is weird. Like,
It is very weird.
would you like me to screen share if I'm allowed to show you the document?
Yeah, because it's I don't know if you guys wrote this down, but I'm gonna clean it. I'm gonna post the recording anyway, but before we get out of here, let me see if I can clean it. So
Yeah, the one you posted on Blackboard, it has like 5 pages on it.
okay, so you're saying that it's not like this?
No, it doesn't. It doesn't have the calculations at all. It's only 5 pages.
What calculations? These calculations?
Yes, those
Yeah.
calculations.
It doesn't have it?
It
No,
doesn't
it doesn't have
any of
it.
this.
It stops before the two, where we have to analyze the two tools to measure. It doesn't have that.
Let me stop sharing this. Let me go. Okay, hold on. I'm very surprised. Let me go to the where should I go? I go to the website of Cal State. Password. Sign in. Okay, Blackboard. Okay, now let me see if I can share the screen with you guys. Okay, share screen. And okay, now I'm gonna go into courses. So you guys see the screen?
We can see it.
Yes.
Okay.
Yeah, we could see it.
130.81. Here's my announcement yesterday. Here's content. And right here, measurement. And it says download it. So I'm gonna download that into, let's say, the desktop. Save. And I'm gonna open it. So far is the same, right? Here's the same. Uncertainty. Oh, you're right. Huh. How come yours is different than mine? I didn't, when I uploaded it into content, I didn't examine it because I assume it's the same thing that I have. Okay. I am going to upload exact same thing that I have so that you can use it.
I think you probably could try to upload it as a PDF. It's probably something with Blackboard, the way it interprets documents, especially Word docs sometimes.
So you think Blackboard does it?
Yeah, because
Okay, let me see, how can I get around that problem? I can email my version to all of you separately. Would that work?
yeah, I think it
Yeah,
would work.
that could work.
Yeah, that could work.
Okay, I'm gonna email my version to all of you separately, and you can just take it from there. Okay. Yeah, it doesn't explain here how these are done. This is completely different. Okay, yeah, you don't have to do this one. I will email each of them to you separately so that you all have it. Okay? Any other concern or questions you have? So you know what you have to do? You just follow what I did, and the last part is plotting the data which was given to you, and it makes you to use the tutorial to basically practice and then calculate the uncertainty and the propagation of error. That's really all that there is to it. And then if you have questions, you can email me. And also this Friday, I'm going to be available from that time that I told you, from 2 o'clock to almost 4 o'clock, that you can, I'll be on Zoom. And if you have questions, you can come and ask me questions. Now, I think somebody was about to ask a question.
Excuse me, yeah, sorry. So no, just one question. So like when you send it to us on our through our emails, then we just send it into Blackboard.
Yeah, the one that I will send to you, it has, as you saw, it has those numbers, and you can just calculate it right there. But it also has the actual thing that you have to do later on. It gave you a bunch of numbers on, I think it was again, distance versus velocity. If you want, I can bring this back up again. and it wants you to actually plot it. So you got to plot it, and then you can email it to me in the form of just Excel. And if anything else you gotta add to it, you can PDF it and send it to me as PDF, or you can send it to me as JPEG, as a picture, and I will see it. So in any format, I should be able to open it.
If that's also the case, how would we be submitting it if there's no submission box at the moment for the lab?
Yeah, I haven't done that yet. I will do it in next couple of days.
Okay.
Yeah, and then when you go there to your Blackboard site and you navigate through it, I may even send you an announcement to tell you where it is, so you can find it and then submit it to there.
Okay. Thank you.
You're welcome. Any other question or concerns? Okay, as I said, don't hesitate to contact me via email if you're confused about something, or if you don't know what to do next. Okay. All right. Have a good rest of the day, and I will see you all again next week. And I'm gonna upload next week's experiment, so please study it ahead of time. And it's gonna have simulation, so you will be able to do it. And I'm gonna do it for you, one example, and then you take it from there. Have a good night.
You too. Have a nice night.
Have a good night,
Thank you.
Professor.
Night, everybody.
Bye.
Bye-bye. Bye.